Hello everyone. Today we will formally start the course and I will start with module 1. The module 1 is about introduction of geometrical optics and ray theory, Fermat principle, refraction from single and double interfaces. Today we will talk about introduction of geometrical optics and a part of ray theory. Now, what is a wave? Then these questions brings some oscillations in our mind. Whenever we say wave, then the waves in a sea appears to mind. The way we when we wave our hand holding a rope, then this appears to our mind. Then the most basic definition would be wave is a disturbance. This is the shortest and best definition. Okay. But formally, if you want to bind these words in a best possible way, then it would be like this. A classical travelling wave is a self-sustaining disturbance of a medium which moves through space, transporting energy and momentum. Okay. Now, these waves are of two types. The first one is mechanical wave. Sound is the best example of the mechanical wave, and second is electromagnetic waves, where our visible light falls. Okay. Now, mechanical wave, these waves require medium to propagate, and these waves are subdivided further as longitudinal wave and transverse wave. In longitudinal wave, the medium is displaced in the direction of the motion of the wave. Sound waves propagating in air comes in this category. Okay. When we speak, then contraction and rarefication of air happens, and through this contraction and rarefication, this sound energy propagates and then it goes to our ears, then it resonates with our eardrum and then we hear the sound. Now, the second kind is this transverse wave. In transverse wave, medium is displaced in a direction perpendicular to that of the motion of the wave. If you drop a cork ball in water, the dropping of pebble will generate water waves, and this surface wave will make the water move up and down, and this wave propagate radially outward. And if you drop a water cork ball, then you will see that due to this movement of the wave, the cork moves up and down slowly, and this represents that the medium is displaced in a direction which is perpendicular to the motion of the wave. The wave is moving radially outward in the water at the water surface, and the cork ball is moving up and down. This is an example of a transverse mechanical waves. Now, coming to the electromagnetic waves, which is what we will be studying about in this course. These waves do not require any medium. Since there is no association of the medium, the wave will propagate with a very high speed, and this is why the speed of electromagnetic wave is very huge, and which is generated by which is described which is represented by C, and its value in vacuum is 3 into 10 to the power 8 meter per second. Okay. And as I said, disturbance advances, not the medium, and since this medium does not necessarily require a medium, it propagates very fast. Now, whenever we say wave, this harmonic wave comes into our mind, this sinusoidal wave comes into our mind, and all types of waves are represented by some wave function, and this wave function is given by this expression psi. Psi is the wave function, and this wave function psi is function of position variable x and time variable t. Now, this wave function at t is equal to 0 would be represented by psi as a function of x. Since it is a harmonic wave, or since it is a sinusoidal wave, generally we can write it as a sin kx. Okay. Now, you may ask that initially there was no k, how come k is appearing, how come a is appearing? A represents amplitude of the wave. Okay. Now, the insertion of k is necessary. Why? Then if you take sine of x, then this would be not allowed. Why? Because x is a dimensional quantity, x is distance, x is length, and you cannot take sine of some dimensional variable. You will have to make it dimensionless. And how to make this x dimensionless? You will have to multiply x with 1 by length unit. Therefore, k will have unit of 1 by length, and this makes kx a dimensionless quantity, and once it is dimensionless, we can easily take sine of this quantity and we will have something. Okay. It is now allowed, and therefore, we can see that a sin kx is a function which is x dependent, x is a variable here. Now, if you vary x and see how does psi look, then you will find this type of curve which is given in blue here. This is a sinusoidal curve. Now, the general expression for a wave is a sin kx. Okay. But we know that a wave moves in space, okay, and since a wave is moving, it must be having some velocity. Okay. All short of wave are represented by some wave function, and these wave functions, this evolution of the waves is governed by a certain type of mathematical expression which we call wave equation. And what is the form of wave equation? Wave equation is represented like this. This is the wave equation. This is a differential equation which is linear, homogeneous, second order partial differential equation. Okay, it is a linear homogeneous second order partial differential equation, and all kinds of wave function obey this second order partial differential equation. They constitute the solution of this equation. Okay. Now, as we discussed before, since a wave is moving, therefore, velocity v must appear in the expression of wave function. How to insert the expression of velocity in the expression? Just by replacing x by x minus vt. V is the velocity, and this x minus vt will now introduce the expression of velocity into the wave expression. Now, in this expression, if you replace x by x minus vt, then we will get this, okay, which is a function of x and t both now. Okay. Now, the resultant wave function will look like a sin kx minus vkt, and this is sinusoidal both in space and time. This expression is periodic both in space and time. Okay. Since there is a periodicity in space, we can define or we can name this period, and in spatial domain this spatial period is known as wavelength, and this wavelength is expressed by a Greek letter lambda. Okay. As I said, the wave repeat itself after lambda. Therefore, if you add or subtract lambda in x, the resultant expression would be unaltered. Okay. If you add or subtract lambda in x, it would not cause any variation into the resultant expression. Okay. Now, we know that psi is a harmonic function, the wave function is harmonic, and by adding or subtracting lambda there is no variation in the expression. Then what we can do is that we will write this wave function and then we will add and subtract lambda in this. Okay. And we also know that in the expression of sine, in the argument, if we add or subtract 2 pi, this will also not cause any variation. This will also not alter the argument of the sine function. Therefore, this would be equivalent to sin k x minus v t plus minus 2 pi, because sine is a cyclic function. If you add 2 pi in its phase, it would come again to its original value. Therefore, this should not make any variation in the resultant function. Now, if you compare the argument of the two, then we will find that mod of k lambda is equal to 2 pi. What is lambda? Lambda is a spatial period which is having the dimension of length and which will of course be a positive quantity. What is k? K is a parameter which is having the dimension of 1 by length, inverse of a length, therefore, it would also be a positive quantity. Therefore, we can safely remove this mod and therefore, we can write k as 2 pi by lambda. Lambda is having the dimension of length, therefore, k would be having the dimension of inverse of a length, okay, which is aligned with the initial definition of the k. Okay. And this k is called wave number. Okay. Now, since the wave function is periodic both in space and time, and here we have studied the spatial periodicity, let us now analyze the temporal periodicity. Now, let us assume that temporal period is tau. Tau is the temporal period, it means the wave takes tau time for completing one cycle. Okay. Now, if you add or subtract tau in time, then you should also end up to the same expression, because tau is the time period in time or periodicity in time. Therefore, we will just applying the same analogy what we have used in case of spatial analysis. Sin k x minus v t would be equivalent to sin k x minus v t plus minus tau, and since it is a sinusoidal function, this would be equivalent to adding plus minus 2 pi. Upon comparing these two arguments, we will get mod of k v tau is equal to 2 pi. Again, k is a positive number, as we have already discussed. Tau is time, positive quantity, v is positive number. Therefore, we will get k v tau is equal to 2 pi. K v tau is equal to 2 pi. Now, in the last slide we saw k is equal to 2 pi by lambda. Substituting for k leads to this expression, which is 2 pi by lambda v into tau is equal to 2 pi, and from here we can get the expression for tau, which is time period. Okay. Therefore, in equation 13 we see that tau can be defined as the ratio between lambda and v. The ratio of lambda to v gives the expression for tau, and the inverse of tau defines temporal frequency nu. Okay. I would also like to mention here is that k is also called spatial frequency. Okay. And inverse of tau is our temporal frequency. Okay. Once temporal frequency is defined, now tau is measured with tau is time, it is measured in seconds, hours and so on. Now, if tau is measured in second, then the unit of nu is hertz, which is inverse of second. Now, from equation 13, which is in our last slide, where tau is lambda by v, we can write velocity v is equal to nu into lambda. Nu is our temporal frequency and lambda is the wavelength. Okay, this is a very important relation. Now, apart from these terms, another very important term is angular frequency, which is often used in optics. And how angular frequency is defined? It is analogous to k. Angular frequency is defined by inverse of tau, but it has 2 pi term in the numerator. Okay, omega is defined as 2 pi by tau, and we know that 1 by tau is equal to nu, therefore, we can write omega is equal to 2 pi nu. Okay, now we have so many definitions. We defined k, which is wave vector, we defined omega, which is angular frequency. Therefore, we can write the initial expression, this psi is equal to a sin k x minus v t in terms of k and omega. Okay. Now, if you write it in terms of k and omega, then the final expression of the wave function would be like this: a sin k x minus plus omega t. Okay. What does plus and minus represent? Plus and minus represents the direction of the wave. If it is propagating in whether it is propagating in positive x direction or it is propagating in minus x direction, it is defined or taken care of this minus and plus symbol. Now, here we see that this wave function have only one frequency omega, and such a wave is called monochromatic wave. Okay, a wave which has only one frequency, single frequency, is called monochromatic wave. But in practice, it is impossible to have a monochromatic wave. All the waves have certain bandwidth, and these waves are called polychromatic wave. Okay. But if this bandwidth is very narrow, then these wave is very close to be a monochromatic one, and these are called pseudo monochromatic. Now, once we have defined all this, we can move on defining phase. What is phase? Now, the argument associated with the sine function is called phase. Okay. And if we want to understand it figuratively, then if you plot a sine function, then this is the type of the plot which we get. Okay, we see that the sine function is start with the 0, it is a 0 here on the horizontal axis. Then we see that the sine function is start from exactly from 0, and therefore, we can say that phase here is 0, but sometimes a wave may start from not from 0, but from certain value which is not equal to 0. Okay, and this decides the phase. What is the value at the beginning here? But more accurately, phase is a relative concept. It is always measured with respect to some reference value. Like here in this first case, the reference value is 0. Okay. Here the reference value is again 0, but there is a deviation here. Okay. And then you can see that this is deviated by pi by 2, and therefore, the phase here would be pi by 2. Okay. Anyway, let us go with the definition of phase here. The phase phi here is defined as kx minus omega t. Now, at t and x is equal to 0, we can define the wave function which would be 0, because when both x and t are 0, the sinusoidal function would be 0, and therefore, the wave function would be 0. Okay, therefore, we can see that phase plays a very important role here. Now, when both x and t is equal to 0, then this correspond to this point. The wave function itself is 0, which is here, but here when phase is equal to pi by 2, the wave function has certain non-zero value. Okay. But generally, in addition to kx minus omega t, there is some extra term epsilon people write along with this kx minus omega t, which is called initial phase, because when both x and t is equal to 0, the waves should look like this. But sometimes what happens is that even at x and t is equal to 0, waves start from this point, and here it means that some non-zero phase is there at the beginning. This non-zero phase is represented by this epsilon. This non-zero phase is also here. Okay, once we know what a phase is, what a wave, what is omega is, what a k is. Now let us define phase velocity. Now we have this expression of phase phi, which is kx minus omega t. Now let us take time derivative of this phase keeping x constant. If we take time derivative of phase keeping x constant, then since phi is equal to kx minus omega t, kx minus omega t, then del phi by del t would be equal to minus of omega, because we are keeping x constant, and if you take the mod of this, then you will get omega. This is what is being represented here. Similarly, if you take the space derivative of phi keeping time constant now, then you will get k from the same expression, this expression. Okay. Now, if you divide this and this is coming here in the numerator, this is in the denominator, then we will get del x by del t at constant phi. This quantity is called phase velocity, and this represents speed of propagation of the constant phase. Now, we know that phi is equal to omega t minus kx or kx minus omega t, and if you take the time derivative of this quantity, then and keeping phi constant, here it says that we are taking time derivative of x and phi is kept constant. Okay. And if you treat phi as a constant and take the derivative of this phi with respect to time, then this term would be 0. Here you will get omega, and here you will get minus k, and from here you can calculate del x by del t at constant phi, which would be equal to plus minus omega by k, and this is defined as velocity or phase velocity. Now, here we can also talk about the refractive index. What is index of refraction? Usually people define refractive index n as c, the speed of light in vacuum, by v, speed of light in a certain medium, and this ratio gives index of refraction or refractive index. The v which is used here is this v, the phase velocity. Okay, and this definition is valid as long as our wave is monochromatic. Okay. Now suppose we have more than one waves, or we have more than one wave functions which overlap in space, then what will happen? What would be the resultant of this? This would be decided by superposition principle, and this principle says that if psi 1 and psi 2 represents two separate solutions of the wave equation, or if psi 1 and psi 2 are two wave functions, then psi 1 plus psi 2 is also a solution of wave equation, or we can say that if psi 1 and psi 2 are two disturbances which are overlapping in space, then the resultant disturbances would be the addition of the two, and this is what is being written here, the resultant disturbance at each point in the region of overlap is the algebraic sum of the individual constituent waves at that location. Now, here this is what is written here is shown schematically. With the blue color we show wave function psi 1, and with the orange color we show a wave function psi 2. The wave function psi 1 is here, wave function psi 2 is here, and with this yellow color the resultant is being expressed. Now, we see that resultant is sum of psi 1 and psi 2. Okay. And we see that all these waves start, they are in phase. In what I mean by saying that the waves are in phase means the crest and trough of these waves come at the same time. All these waves start from 0, the initial phase is 0 here, and they passes through their maxima and minima simultaneously. But if we consider the opposite case, then what will happen is shown here in this diagram. Again the blue curve represents the wave function psi 1, the wave function psi 2 is given by this color, and the yellow color represents the resultant. Now, here you see, what you see is that the blue color and this red color is opposite in phase, and therefore they cancel out, and therefore the resultant which is given by this yellow color is of very low amplitude, while here the resultant is of very high amplitude. It means the resultant will always depend upon the relative phase of the waves which are overlapping in time or which are overlapping in space. Okay. This is all what superposition principle tells. Now, it is while doing mathematics, it is always very easy to move to complex domain. Therefore, in this slide we will learn how to represent a wave function in complex representation. Now, we know that any complex number can be expressed as x plus iy, where x is a real part, y is imaginary part. Okay, and I is iota, which is equal to square root of minus 1. In polar coordinate, this can equivalently be written as r in bracket cos theta plus I sin theta. Okay, and this can equivalently be written this cos theta plus I sin theta be written as e to the power I theta. This all we know. Therefore, complex number which is expressed by z tilde, it can be written as r e to the power I theta, and which would be equal to r cos theta plus I r sin theta. If you want to calculate the absolute value or the modulus of this complex number, then you have to take the mod, and this mod will be equal to r. R is modulus of z tilde. Now, how to calculate complex conjugate? Now, to calculate complex conjugate, you will have to just replace iota by minus iota. Therefore, here at the in the exponent I is replaced by minus I, and here in this form I is again replaced by minus I. This represents the complex conjugate of z tilde. Now, z tilde, which is a complex number, as I said before, it consists of a real part and the imaginary part. The real of z tilde is expressed as x, and imaginary of z tilde is y. Now, with these informations, we can write our wave function in complex note form. How to write this? We know that our wave function is expressed as a sin kx minus omega t, or psi is equal to a sin omega t minus kx. The minus sign will just alter the phase. Okay. This is a real part. If you plot it, you will see some variation here, but how to go to the complex domain? We will follow this, that a complex number can be represented as r cos theta plus iota into r sin theta. Okay, and then once cos theta, sin theta and r is known, then everything can go into a complex notation which is r e to the power I theta. Okay, and the real part of this complex number is r cos theta, which will represent our wave function. Okay, knowing this, we can represent our wave function here. We have a e to the power I omega t minus k x plus epsilon, which is our wave function, which is written in exponent complex form, but the imaginary part of wave function does not hold any significance. It is the real part which is of our interest. Therefore, we put r e here. The real part of a e to the power I omega t minus k x plus epsilon will represent the wave function. Epsilon is some arbitrary phase. If you take the real part of a e to the power I omega t minus k x plus epsilon, you will get cosine function, and this is which you will get cos omega t minus k x plus epsilon. Now, this is all for today. Now, in the next class we will move further in the module 1, and we will learn about the ray theory and then Fermat principle. Thank you.